Third installment in Work and Power, Part 3. Looking at work done, of course, against gravity. Often we're lifting things up. That's really what work involves, lifting things up against gravity. So if we take a look here, work is equal to force multiplied by displacement. And of course, the force applied is lifting an object up against gravity. So if you're lifting something up at constant velocity, that must mean that you're exerting a force equal and opposite to Fg, the force of gravity. Initially you'd have to get started, but moving it up constant velocity, the force up and the force down must be equal and opposite. So that force that we need to apply is equal and opposite to Fg. So that's interesting to look at when we're lifting up things off the ground. So for example here, how much work is done in lifting a 5.0 kilogram object 1.2 meters off the ground? So we could use this idea. You have to envision, are we pushing something on a level ground or are we lifting? In this case we're lifting. So we'd have to use this idea. So if we take a look at known variables here, we have our mass is 5.0 kgs, our displacement is 1.2 meters off of the ground. Of course, little g is negative 9.8 meters per second squared, as always. So we're lifting something up. The force, the applied force, and the displacement are both in the same direction, so we have positive work here. The object is going to gain energy. As I mentioned before, work is equal to the change in energy. It'll gain kinetic energy because it's absorbing that work that we did. So work is equal to force times displacement. So we can think of it as the opposite of Fg. I'd have to offset that. So over here, I just did that over on the side here, figuring out the applied force I would need to do. So force is equal to the negative of mass times gravity. The mass is 5.0 kgs. Gravity is negative 9.8 meters per second squared. So I get negative, negative, positive 49 there. Easy. Then just simply put that back in the equation. The applied force is 49 newtons, acting 1.2 meters. So 58.8 newton meters. Of course, 2 sig figs here throughout, so 1 sig fig, 2 sig figs, that's an 8. So that gets bumped up to a 9. So 59 joules. And we can say that we get a positive answer there. So the object is gaining 59 joules of energy. You're applying 59 joules of energy, the object gains 59 joules of energy. Okay. What about if we simply take that object and put it back down on the ground? How much work is done in lowering it back down? This is kind of an interesting case because we're still applying a force upward because we're holding the object up, but we're slowly bringing it down. F and D are complete opposite directions. We're holding it up, but releasing it down. So we have to note that force and displacement are opposite directions. So when looking at this, if we consider this direction as positive, lowering it through a negative distance, well, the displacement will be negative, so we have 49 newtons multiplied by negative 1.2, and we get negative 59 joules. Now, that's not direction. A negative work value means that the object is losing energy. So it's the opposite case. So gaining 59, losing 59, because the object is approaching the ground. Okay, so once again, be careful with the work there. Positive and negative work values pertain to whether the object's gaining or losing energy. And lastly, with this little segment here, I'd like to look at comparing work done vertically versus angled and seeing how that relates. So I picked a real easy case here to sort of prove something. Looking at a 3-4-5 triangle. Okay, so 3 meters by 4 meters by 5 meters. In order for that to be true, this angle here would have to be 36.9 degrees. And of course, using geometry here, if I had a mass sitting here, Fg would be pulling it down. I have F perpendicular, which is equal and opposite to the normal force. And I have F parallel, which is equal to FA. Okay, so I'm going to deal with two scenarios here. I have a 6 kilogram object, and I'm going to look at how much work is done in just simply lifting this. So the idea is to get the object to here, up to the top of there. How much work is done in simply lifting that object from here to here? How much work is done in moving it up the inclined plane from here to here? So we'll look at that and see what kind of difference results in that. So if I look at pushing it up, first of all, we'll assume it's a frictionless plane. Otherwise, we're going to run into other issues there. So we have earlier in the friction unit there, F parallel is equivalent to FA. So if I can figure out F parallel, that'll give me FA. Quite easy. So looking at this triangle here, F parallel is the opposite side, FG is the hypotenuse, and the angle there is 36.9. So if I take a look at that, the sine of 36.9 is equal to F parallel over FG. Multiply each side by FG to get F parallel isolated. And I get it to be 35.3047 newtons before rounding off. And if I figure out the work done, therefore, in pushing it up, and one thing to note here, FA is this way, so in order to push it up, assuming no friction, I have to exert an equal and opposite force in this direction, because we're assuming there's no friction. We're making it a very easy question, relatively easy to calculate. So FA is applied that way. So if I take a look here, I have W is equal to force times displacement, so my 35.3047 newtons, and I'm moving it up the inclined plane, which is 5 meters. So that works out to be 176.52 Newton meters. And all these numbers, I believe, are 2 sig figs. So keep the 1, keep the 7, that's a 6. So that gets bumped up to an 8. But to ensure that that stays in the 100s place, I need to have a placeholder 0, 180 joules. Okay? Comparing that to simply lifting the object up. 6 kilograms up 30 meters. So W is equal to force multiplied by displacement. And of course, we're lifting something up against gravity. So the force we need to pull up with is equal and opposite to Fg. So I could just simply, to make things easy, instead of calling this Fg, I know that Fg is mg, so let's simply put that in. W equals mgd. So if I look at that, 6 kilograms opposing gravity, positive 9.8, 3.0 meters, 176.4 joules, and look at that. I get the same amount of work there, 180 joules. So it takes the same amount of work to lift an object up to there as pushing it up there. So of course the main difference that you see here is the forces. To push an object up the incline, it's 35 newtons approximately, and over here we'd be looking at maybe around 60, just slightly under 60 if I take 6 times 9.8 there. So it's easier, of course, to push something up an incline than to lift it straight up, but even though the same amount of work is being done.